how can I stop sharing?
There is an X button. Okay, all right. Okay, Assalamualaikum and a very good afternoon, everyone. Before we start, let me play you the introduction video of our conference.
IEEE Telecom is a leading global managed internet and SD-WAN provider with offices in Cyberjaya, Jakarta, Yangon, Hong Kong, Singapore, Washington, D.C., and San Francisco. We are equipped to cater to your global business needs. Leverage our vast network of 1,000 plus partners, over 10,000 services, and bespoke customized solutions. We use the latest technologies to provide first-class global internet, SD-WAN, and managed service capabilities. No matter your industry, our team of highly experienced experts are ready to elevate your business network and ignite your digital transformation. At IEEE, we cover a vast range of industries: airline, oil and gas, finance, education, retail, FMCG, logistics, manufacturing, telecommunication, government, and many more. Set your business apart with our unique global coverage in over 200 countries and territories. One-stop shop solutions, 24/7, 365 network monitoring, up to 99.9% SLA, and global awards. Our team of experts make us the funkiest telco operator in town. With multiple in-house facilities and activities, we have exemplary work-life balance to promote productivity, creativity, and a homely spirit. Want to know more? Visit our website at www.iextelecom.net.
Okay, that is a little bit of introduction of our Asia Pacific Conference in Communication, or APCC. This is IEEE 26, APCC altogether, and Kuala Lumpur is hosting it this year. This afternoon, we are very fortunate to have Prof. Tarik Taleb. Well, it's afternoon in Malaysia, but it's in morning over there. Hopefully, it's not still too early in the morning. Prof. Tarik, before we start, let me introduce Prof. Tarik a little bit. This is what has been prepared by Dr. Fazirul earlier. So I'm sharing whatever that he has shared with me. So this keynote speech number 2 will be by Prof. Tarik, Taleb from University of Oulu, Finland. Hopefully I pronounce it correctly, Oulu. The topic is going to be on 6G, the journey towards a new breed of cloud-native mobile networking, although we are still trying to embrace 5G, and even in Malaysia, 5G is still not there yet. But people already in research are talking about 6G, so we're going to look at this journey to this new brief. I think the biography of Prof. Tarik is very colorful. I think he has been an impressive there have been some impressive recognitions that he has got so far. He's currently the professor at Center of Wireless Communication, University of Oulu, Finland, professor at the School of Electrical Engineering, Aalto University, Finland, and founder and director of the Mosaic or Mosaic Lab. .org, and he used to be a senior researcher and 3GPP standard expert at NEC Europe in Germany, assistant professor at Tohoku University, Japan, and research fellow also in Japan. So his research interest is mostly on network softwareization and slicing, mobile cloud networking, network function virtualization, software-defined networking, mobile multimedia streaming, and cloud computing. He's also the general chair of WCNC 2019 that was held in Morocco, and he has been involved in a lot of the IEEE flagship conferences, as well as the editor-in-chief of some of the well-known IEEE journals, especially in communication. So he has received various awards from IEEE, especially IEEE ComSoc. There has been 2017 up and as young as early as 2003 when he received the Young Researcher Encouragement Award. I'm lucky to meet Prof. Tarik back in 2015, I think, when we held the MICC in Sarawak, and he was the keynote speaker then. I still remember that talk because it was on NFV, network function virtualization, so it's still fresh in my mind. So without any further ado, I will stop sharing here, I'll stop talking, and let the keynote speaker to do his talk for today. So the floor is, or the windows is yours, Prof. Tarik.
Thank you. All right, so I will be sharing my screen. So can you see my screen?
Yes, very clear.
All right, so I'm using only one screen, so I just see my slides. I don't see any interaction on this, on the conference tool. So if anybody has a question, please feel free to interrupt me and ask that question. I mean, in the middle or towards the end. Okay, so it's first of all, I really would like to thank everybody. I mean, the organizing committee of the 26th edition of Asia Pacific Conference on Communications for giving me this opportunity to deliver this keynote and share with you some of my thoughts on, what I would say the journey towards 6G. You're absolutely right, Professor Yusuf, that many countries, not only Malaysia, they're still struggling to deploy 5G. Actually, 5G was very ambitious, as I will be demonstrating in this keynote. But in the research area, at least, we started talking also about what would be this beyond 5G or 6G system. So the title of my keynote is Towards a New Breed of Cloud-Based Networking. And in my humble opinion, there will be a lots of changes happening in the concept of networking, in the way how we have been studying and how we have been teaching networking, in this era of beyond 5G or 6G. So before we go into this journey that will hopefully lead us to 6G, or I'm trying to be careful not to call it even 6G. Maybe sometimes I will refer to it as beyond 5G, sometimes as 6G. This is just the beginning, and everybody has his or her own thoughts of how the system should be designed. And here I'm just sharing some of the thoughts that I personally have, as well as I've been discussing with the colleagues that I have in the University of Oulu, as I will be introducing later. But before we get into that journey, let's look at the current stand of 5G. What is 5G? 5G has been intended to be deployed by 2020. Some countries have deployed 5G, but as we will see later, the core is still 4G, and base stations are 4G, but boosted a little bit with some new radio, 5G G-Node-Bs. So here I will list up some of the fundamental challenges, I would say, that have been hampering, the deployment of 5G as we thought of it, let's say, in the beginning of, in 2011, 12, 13, when 3GPP was defining the requirements of 5G, 3GPP, ITU-T, different standards bodies. So the number one challenge, in my humble opinion, is there is a challenge in business model with 5G. As you know, 5G is designed not only for individual users, but also for verticals, for over-the-top service providers, basically entities that will bring not only one single individual user, but a huge mass of users. But when we talk to verticals such as automotive, such as UAV operators, or over-the-top service providers such as Google, Facebook, and so on, when you talk to them, they're not willing to buy the service. They're not willing to pay for the connectivity service. Basically, they want to have the connectivity service provided somehow as a free lunch, to their end users. And of course, these companies, they are very good at generating revenues out of advertisement. So the business model is very challenging. The other problem which is facing 5G is the fact that still, the companies that are in the area of telco, like network equipment vendors or even mobile operators, they still adopt, this old business style where they sell boxes and instead of software that could run on any kind of cloud platform, which was not the initial view of 5G, but it became the vision of 5G, as we will see. So and the architecture itself has been tied to the 4G model, and hopefully I will touch upon that, in the next few slides. In my humble opinion, one of the most important challenge of 5G is the difficult regulations that are actually facing, those vendors or those verticals that were actually expected to use 5G. For example, I think you have seen a lot of white papers, lots of even scientific publications that speak about 5G as being the enabler of UAV operations beyond visual line of sight, or self-driving vehicles, and so on and so forth. But just let's be honest with ourselves and ask, how many self-driven vehicles do we see in the road? How many UAVs do we see flying in the air? Not many. And those, they are not there because they are not allowed to operate yet, because there are lots of issues with regulation, with the legal issues, with the safety, and so on and so forth. And of course, those verticals, even if they are seen as potential, sources of income, for the 5G mobile operators, they are not there doing the business, and they are not willing to even probably pay or buy the service. And that puts, the 5G operators really into very difficult situation, which is, why do I have to invest into a very expensive system when I don't see immediate return on investment? Even it's worse, I have to invest in an infrastructure which is definitely going to be expensive, because I have to buy new equipment, I have to buy new core, new software and new hardware. But at the same time, I am always facing this issue of the average revenue per user is not going up; it's actually going down, or it's it's not becoming very profitable. So this is the issue. And the other problem, in my humble opinion, was actually with the design of 5G itself, because we were so much ambitious in how 5G should look like. I mean, yes, I would say those that have defined the requirement of the service or of the system have done a great job by thinking of something which is too ambitious. But then when it is too ambitious, then it becomes challenging to realize. And latency is one of them. Actually, when we talk about 5G, we speak about a system that should be giving us an end-to-end latency of 1 millisecond. Is that doable? It's very challenging. And unfortunately, we keep on doing the same thing. We keep on just applying these kind of operations, these simple mathematical operations of plus, minus, or division or multiplication, and we say, all right, the next generation system should be 1,000 times more capable in terms of capacity than the previous one. It should be 1/10 of whatever latency we have envisioned for 5G. For example, like we say 1 millisecond end-to-end latency for 5G. Now people, some white papers, they have spoken about 0.1 millisecond end-to-end latency for 6G. I mean, there are two questions. Do we need this kind of latency? And even if we need it, which service would need it, and when this service will be deployed? So all of this, you know, you cannot invest into technology which would be very expensive to realize when you know that there is not much expected revenue coming out of that. And that's, in my humble opinion, really the biggest challenge that we have been facing with the deployment of 5G, and also whatever would be by 2030, whatever we would be calling as 6G. Now, definitely 5G has been known for its three main use cases. I think they were on this slide. Mobile broadband connectivity, massive Internet of Things, or massive machine type communications, or this ultra reliable low latency communications. These are actually the three main use cases. But if you split them into, you know, these key applications or key use cases of 5G, there are actually 6, as you can see on this slide. Now, in my humble opinion, when it comes to massive Internet of Things, when it comes to broadcast services, I think with 4G we can do that, with some kind of traffic engineering, with some kind of engineering of when IoT devices should be accessing the system, maybe not during the daytime, but you can have them access, you know, in the night when there are not too many people connecting to the mobile system. You know, with this kind of tweaks here and there, 4G is, in my humble opinion, capable of supporting these services. When it comes to broadband connectivity, or this enhanced mobile broadband connectivity, mainly in dense areas, actually that is also doable with 4G core, with the 4G base stations, and of course, you know, the radio capacity could be boosted up with the new radio, with the 5G G-Node Bs, you know, the millimeter wave, as I think I will show you in one of the next slides. But when it comes to low latency, when it comes to reliability, when it comes to this mission critical services, I think that is where 5G is. Whatever we have by 2021, by today, that is where 5G is lacking big time. And because of this, if we speak about the beyond 5G use cases, I would say that there are two categories. There are those old category of services. They are old not because that we are all of us enjoying them. They are all just because we are inheriting them from the 5G system. They have not been realized. And there, autonomous driving is one, UAV services is another, tactile internet, industry 4.0, and so on. But then, of course, we have to be, ambitious, you know, for justifying the creation of a new system. And because of that, we are actually also, we start hearing about new services that would need a lot of bandwidth, that would need also this extremely low latency. And here I would bring extended reality services like holographic teleportation, Internet of Everything, Internet of Intelligence, mainly when you have many AI models that have to communicate among themselves and take like decision online, very quick. And also, you know, this digital twinning of environment. So I would say the landscape is becoming much more challenging because of these very ambitious use cases and the requirements that they come up with. So that was in brief about the current stand of 5G and the limitations, let's say, from the requirements and the use case perspective. Now, let's go to the main topic of today's keynote, which is what this networking beyond 5G would look like. And indeed, that will be defining the journey that we will be taking for the next, you know, during this decade, you know, to till the deployment of the first 6G system. Now, every generation we had before is characterized by something. I think you would agree with me that the third generation and the fourth generation, that's actually the system that really enabled us to have ubiquitous connectivity, to have always on connectivity, to have always an IP address which is assigned to our user equipment. The biggest success of 5G, in my humble opinion, is the fact that it could bring expertise from different domains together towards, working towards defining this 5G system. And here I'm referring to the telco world, of course, because 5G, at the end of the day, it's a mobile system, is a telco domain. And also they brought, software engineering, when we talk about softwareizing the network equipments, network function virtualization, and also it brought, the cloud expertise. So these three expertise, they've been working together to define what we have as 5G system, as I think I will show you in the next slide. So in 5G, lots of interesting IT principles have been adopted. Heavy involvement of cloud computing, with all of its different business models, infrastructure as a service, platform as a service, software as a service. And then we have been adopting to a certain extent, although I'm putting on my slide, strong adoption of IT principles, it's strong if you compare it to before. So we've been adopting the concept of microservice, integration fabric, of course, network function virtualization, network slicing, softwareization. And, because of this, we came to this service-based architecture as it has been defined, I think, in release 15 and beyond of 3GPP system. Now, yes, I must admit that a big step has been, taken, towards this service-based architecture, which is defining, the 5G core. So, for example, you can see here that set of network functions. You don't have to know what they are doing, but there are different functions that are actually in the control plane that can communicate among themselves via some kind of integration fabric. It's not like in this style where you have what we call reference point model, where I need to know what is your IP address, and I will say, okay, and then I need to set up the connectivity, the connection, so then I can, talk to you. With this service-based architecture, what I do, I just need to register myself at certain node, which is here network repository function. And whenever I want to discover other network functions, I will go to here and I will say, okay, I want to talk to this node. Where can I find it? And then this one will provide me with the API that I should use so I can actually connect to it. So, with this kind of service-based architecture principle, then I can just throw these network functions on any kind of cloud platform. I need to just make sure that I have a database where I can register them and where they can actually discover each other. And then that will be much easier in terms of configuration. So yes, we have achieved this loosely coupled services. So services, they don't have to really stick to each other and know each other. And that really brings a lot of flexibility in terms of initial deployment and also in terms of configuration during the lifecycle management of the service. Yes, we have also achieved some kind of modularity. So we could split, functions that do just the mobility management and functions that do just the session management. So, and that will give us, lots of freedom in deciding which function to use for what service based on the needs of the service. But then the current SBA system that we have, still, it is not meeting these requirements of true cloud nativeness. At least the data plane still, it is reference point model. It's not extensible. So that means if I get new service, I still need, me as an engineer, I have to do lots of configuration so I can make that service talk to other services. So, and then the network itself is not really open to third parties. So there is some kind of network exposure function here that can speak to an application function or expose certain predefined, information about the network to the application function so it can do certain optimization, but the network itself is not open. So these three things, that's actually where I would say the 5G system as we have it nowadays is lacking big time. And that's really, if we want to have a network which is very flexible, a network service which is very which can be flexibly deployed on any kind of cloud platform, definitely the architecture itself should be revised and should become cloud native. And because of this, of course, many operators, many vendors, they have realized that there is still a long way to go till we achieve that. And that's why actually, if you look at the current deployment of 5G nowadays, they are most of them, I mean, most, if not all of them, they are deployed in the non-standalone fashion, which means that you have 4G base station and 4G core, which does all the control plane. And then if you want to have more bandwidth, at the radio level, then you just use, this 5G G-Node B. But then the core, it's completely 4G, old style, let's say. It's from the 4th generation EPC core. And of course, the intention is to move one day to option 2, where you have a completely cloud native 5G core that can actually manage, the different radios, base stations that, of course, they are 5G or even 4G base stations. Now, when we talk about this 6G system architecture, and if we try to learn from the mistakes or from the limitations that we have actually been facing in the design of 5G, in my humble opinion, the beyond 5G system, I'm trying to be careful here and not call it 6G system architecture. In my humble opinion, it has to be truly cloud native. It has to be entirely service-based architecture. And actually, SBA architecture has been proved to be very efficient when we look, for example, at those major large-scale application providers, how they could actually scale up very quickly and deal with lots of demands. And actually, the SBA is being adopted by companies such as Facebook, such as Google, all of these application providers that are actually dealing with a huge mass of end users, not only in one given country, but at the globe scale. So the beyond 5G system has to be truly cloud native. It has to be entirely SBA based, and it has to be composed of a set of services that are actually extensible. They can register somewhere and they can discover themselves, easily through that entity, which I'm referring here as the service registration and discovery function. And of course, these services, they can be one time, they can be consumer of services from others, and they can know each other just through kind of well-defined APIs, of course, securely. And they can be also service providers when they are being consumed by another service. And this is exactly the true concept of SBA, where you have service. It can be consumer, it can be also a provider. Now, and with this vision, what we would be having, I mean, the 5G, the beyond 5G system architecture, it's going to be just a set of services. I mean, we would probably go beyond that old way of seeing things, network of networks, towards a system which is a service of services, where you have network itself is actually service that could consume services from others, like, for example, from a cloud. And also it can be service which is providing the delivery of data, for the other service. And this will govern, the relationship between the different services that are actually composing, that 6G system architecture. And I will explain this idea, hopefully in more clarity in the next slides. So now, what is this journey that we're going to take towards let's call it the beyond 5G system or the 6G system? As I said, 5G, we have done a great deal in terms of adopting, cloud computing into the design of the mobile telecom system. And I think in the beyond 5G, we will continue on improving more and make the system even much more cloud native. But there are two main things that will be kicking in. Number one is artificial intelligence. I think we would all agree that artificial intelligence is the thing which is needed to automate the network management, to automate the service management. And this is exactly what has been much desired since a long time ago. And we refer to it as zero-touch network and service management. And of course, when you want to manage, you need to sense. And you apply your AI models to decide what to do based on your sensed data. And if the AI say you have to do something, then you need to actuate. And that's why the sensing and actuation capabilities will be also a very important, component or service, of this beyond 5G system. Now, within the 6G flagship program that we have in the University of Oulu, we've been looking into how we can reorganize or how we can redesign this beyond 5G system architecture towards achieving this concept of service of services. As I said, beyond what we have been having up to now as a network of networks. So we have identified actually six main key enabling services, and I will explain the logic behind them. So, of course, you need a service to be provided, and this service is going to be consumed by maybe a vertical or by an end user. And this service needs to have some mobility support, or at least it needs something that's a network which will provide the data itself, deliver the data. So the networking is also a service. This networking could be having its functions running on cloud, or the logic of the service could be running, on the cloud. And this actually brings us to another key enabling service, which is application computing. Of course, we want to be able to automate the management of the service which is running on the cloud and the network which is delivering the data. And for that purpose, you need to understand contextual information about the users that are consuming the service. You need to also understand information about the locality where the service is being consumed or provisioned. And this brings us to two other key enabling services, which is the user context and the local information. And then if we apply different, let's say that we have a huge library of AI models, which could be somewhere, centralized or distributed. That's a different point of discussion. So if we have these AI models, then they can read from this data and then take certain decisions of how to manage, the network, expand it, or how to expand, the cloud resources, or how to activate, the sensors, which could be, at the radio access network and so on. And this will take us actually, as I said, to two other key enabling services, which is the ubiquitous intelligence and activation. So now, of course, like if we zoom into each key enabling service, there are different components, but I'm not going into that much details. But for us, these key enabling services, they can also talk among each other through, via this integration fabric model, where they themselves, based on certain location, they could be specific to a certain location, they could be specific to a certain country or to the whole globe. So the flexibility in designing them to the scale of, or according to the region of interest is there, or it should be coming by the design itself. So these services, they need to be able to register themselves, discover each other, invoke each other, and communicate among themselves, of course, in a secure way. So these are the key enabling services. If you grant them or if you provide them, then you will be able to support any kind of service, any kind of beyond 5G application or service. This means an XR application, a UAV control application, a collaborative robot, an autonomous driving service. So these services, they will be actually consuming services from these, key enabling services. And not only that, actually these services, and this is exactly what we want to achieve with this concept of extensibility, that these services, they should be also able to register themselves and discover each other. And in this way, this service could consume, the service which is coming from another service provider. So basically, there is this relationship of service consumer and service producer, not only among the key enabling services, but also among the services which are actually using, this whole system, 6G system architecture. Now, let's look into this into more details. What does that mean in real life? Definitely, we will be having a complex landscape with the different hardware or physical infrastructure. The physical infrastructure is also technologically diverse. So you'll be having transport networks, you'll be having the radio network, you will be having the cloud network, and each of them, they probably are administrated by the same entity or different entities. And this is basically what we refer to as multi-technology, multi-administrative domains of the physical computing and the network infrastructure. Now, we're not reinventing the wheel here. I mean, of course, in the area of network function virtualization, there has been a lot of work that has been done in defining how these resources, these physical resources, can be abstracted and managed and provided to the users which are actually on top. And this is one of the work that we have done in my research team, which actually describes how this on multi-domain network slicing, orchestration, and management should be done. Now, let's assume that we have this resources being abstracted and provided, to the people or to the entities or to the end users that are actually consuming, some of these resources or all of these resources. Now, we want to provide a service which needs mobile connectivity, or it needs mobile connectivity service. Basically, it's a service which will be consumed by an user equipment which is on the move. So this user equipment, of course, it needs to connect to the radio access network. This radio access network could be just, the way that we have it nowadays, physical, or it could be virtual, or it could be shared. And basically, this is what's happening nowadays, that we have many network slices, at least, in the context of 3GPP, with a run which is being shared. Now, this user equipment is consuming a certain service, and this service, of course, it's going to be transported over a network. And this network, of course, it is mobile network, it's a data plane, the control plane, but everything is actually running on a transport network, which is also could be created in virtual way. Basically, you have set of resources which you can actually get them based on the needs of the service that is being consumed. So you have a virtual transport network, on top of which you can actually create this virtual data plane, which is consisting basically of those software or those virtual network functions, which could be running on the cloud. And they are just, you're using the right type of virtual network functions and the right amount of resources. And they are even being controlled by a virtual control plane, which is also designed, in the same fashion. Now, something else which has not been probably, for example, spoken about, at least in the context of 5G, is that actually you could be having in-network supporting functions. Basically, let's say that this person is actually having this Google glasses or Microsoft HoloLens, and is actually taking some streams of the environment. It doesn't, these glasses do not have enough resources to do the processing. So basically what this device would do, you would stream the data, you would stream the video to, for example, to one of the data plane functions that you have here, which is giving you the IP address. And then you break immediately and you go to a function which is within the network itself, in-network supporting function, which does, for example, for you some kind of object detection. So basically it takes the video and then it processes the video and then it provides you with data, whatever data you are in need of. For example, it says information about the environment you are seeing, or it says, the person that you are, the name of the person that you are seeing with your glasses, and so on and so forth. So these in-network supporting functions could be different things, could be AI models that will process your data, could be things that will cache, your streams. So it depends on the service that you have in mind. Now, the other thing which is interesting, that actually when you do this in a segmented way, in fragmented way, for each service you'll be having some kind of closed loop, the system closed loop, where you can collect the data, you monitor the data, you apply certain analytics, and then based on those analytic engine, you take certain decision, and based on the decision that you take, you activate the decision. For example, you can increase the resources, you can reduce the resources, you can block the person if you see that the person is doing some kind of malicious. But the closed loop is actually specific to this virtual run, and then you can do the same thing, closed loop, which is specific to the transport network, to the data plane, to the control plane, to the in-network supporting function. And then you'll be having the logic of the service running, in a way which is, traditional way, which is at the cloud. It has also its closed loop, and everything is actually managed, adopting, this kind of concept of development, DevOps, development and operation. And I will explain, what that means in a moment. So basically, when we do this, what we are enabling, we're enabling any service developer to create, the service on the cloud, with its specific closed loop, and also the transport networks at different levels, the transport network, the data plane, the control plane, and also in-network supporting functions with their specific closed loops, and the virtual radio access network resources with their specific closed loop. And in this way, of course, like these closed loops, they can communicate, they can take decisions which are just specific to them, or they can coordinate among themselves, so they can take a decision which is optimal to all the players, that are actually involved into that end-to-end communication. So basically what we are doing, we are extending the concept of cloud computing beyond data centers. Instead of having, for example, let's say that I'm using Gmail, so I can have my emails which are actually being processed in Google data centers, but then the connectivity is coming from different players that I'm not even aware of, different mobile operators, different transport network providers. What I'm doing, I'm actually extending the concept of cloud computing beyond data centers all the way towards mobile end users. And in this way, what I'm doing, I'm providing actually the service itself. The service logic is also running on the cloud, but the network which is delivering the data itself, it is also provided as a network service. And I can do the network service for production, and I can do also network service for development and testing. So basically, DevOps have been used very intensively, in the design of services, that are running on the cloud, but the network has been completely outside, the scope. But with this idea, we can actually have, I can have resources of the network services which are good for the production, but then I can do different testing, for my application, and then I can test whether, those upgrades that I have made, they are also good. What kind of network service type that I should be having, so it will be good for them. And this is basically the network service that I can have extended for development and testing, another one which is operating in an isolated way just for the production. And I can do this for service number 1, service number 2, service number 3. And with this way, what I'm getting the mobile connectivity, I'm getting transport networking, in-network computing, decentralized computing, smart storage, and even these DevOps features, everything is offered to me as one atomic end-to-end service. And it comes with all of these interesting things of these interesting features which come with cloud nativeness, which is on-demand elasticity, multi-tenancy, and pay-as-you-go, basically the cost efficiency. Now, when we have these services, actually, they are registered with specific APIs at certain point, and they are talking to each other, via this well-defined integration fabric. Then this is exactly how I can really achieve this service extensibility and adopt truly the concept of service consumer, service producer, in the whole design of the system. So with this, we can also achieve this through network openness. As I have said earlier before, nowadays what we have the 5G service. The 5G service provider is having its service, service logic and the database, of information elements about its users or about its service, at the cloud. But then the network which is delivering the service is completely not belonging to the service provider itself. But with this concept, what we're doing, as I said earlier, we are expanding these administrative boundaries of the service provider from not only the data center, which is storing the service logic, towards also the network itself is also administrated by the service provider. And in this way, we are really opening the network. And I think with this, lots of innovation could be achieved. And only one's imagination can be limited to what we can do with this. Now, that was somehow, the concept of 6G system architecture as we see it, a service of services. And with this, basically what we can achieve, we can have services depending on the requirement of the service, depending on the locality of the users. We can have these services even deployed, very close to the end, to the end users, leveraging, this kind of edge cloud, and there are different layers of edge cloud, near and far edge cloud. But still, we have this problem of extremely low latency and reliability, which we are actually in need of. And there are actually applications which are actually in need of this kind of latency which is single-digit latency, like 2 millisecond, 1 millisecond. So here, for example, this autonomous driving, they're talking about end-to-end latency, which should be less than 5 millisecond. And indeed, this is very important because it is actually a life-threatening service. If the system doesn't take quick decisions and stop, for example, the car when it has to, any delay can cause serious damage that could even go up to the level of causing the death of somebody. Same thing with industry automation. There are certain latencies which are actually very strict, extremely low latency, depending on the operation of on the industrial application there. And also there are services which, if you want to have that true immersive experience, like in the context of AR, VR, or holography, the end-to-end latency should be really single-digit latency. So it should be 1 to 9 millisecond, or in some cases even a fraction of 1 millisecond. Now, there are lots of ways of achieving the end-to-end latency. The straightforward solution, as I said earlier, is putting the service, at the edge. But even when you put it at the edge, the packet of the service has to go from the user, to via, for example, the base station, via certain switches and the routers, till it reaches, via the data plane functions, till it reaches, the service which is running in the edge cloud. So without any kind of queue management or proper queue management, certain services that are actually extremely low latency sensitive, they would face some issues, and their packets may be dropped even if you prioritize them, in a static way. Actually, one way that we have been looking into is to avoid these conflicts, which could be between even the real-time data flows, that means the ones which are actually latency sensitive. We have been looking into how we can create queues, not queues that are actually created already in advance, but based on the situation that we have, using some kind of AI models and so on, we can create a queue, at certain switch, and we can even direct, the packets of that flow to go via the highly prioritized queue. So, for example, I could have highly prioritized Q1 and then just best effort queue. But then if I see that the situation needs to create another queue, so my packets will go via another queue, so I can, I can achieve that end-to-end latency which is needed by my service. I should be doing it in what we are referring to as software-defined queuing. So it's not only software-defined networking where I set up to the flow, I say go via this switch and that switch and that switch, but here I would even say go via this switch, but within that switch you have to go via this particular queue. If that queue exists, I will just say go via that queue. If it doesn't exist, then I can remotely create it and direct, the packets to go via this newly created queue. That, in my opinion, will be the best, to achieve that end-to-end latency. And then, in addition to that, even if you do this, there are certain mistakes that could happen when you don't do the queue creation. They are not done, in the right way. Then there is need to even look more into the way how packets are being actually processed within, the switch, within the queue itself, by having like much more suitable flow scheduling and traffic shaping, which are actually implemented locally within the switch, so you can ensure that deterministic quality of service. And we have done that. We have been looking into, because things are not predictable. You don't have, things can, when you can predict how things will evolve in time, then you can have some policies which are actually pre-installed and then just enforce it when the situation is faced. But when you cannot predict much, then you have to use AI models that actually do not depend too much on the prediction. And here we have been looking into how we can leverage reinforcement learning to do this kind of flow scheduling and traffic shaping, so we can actually accept as many flows as possible and meet, their deterministic requirements in terms of latency. Any system that you build, any mobile system that you build, it's actually built on top of a transport network. And here, to meet that end-to-end latency, which is needed by certain deterministic services, as I mentioned earlier, there is need for very tighter integration with the transport network. And here also we've been looking into, I can create the control plane, for example. I can create, the user plane of the mobile network, but that means I will put, these virtual network functions at certain edge data centers or at certain, core data centers, centralized data centers. But these are actually connected, they are connected on through, an optical network which operates in a completely different way. And here we've been looking into, for example, how we can reflect latency in the definition, when we define, that service function chain, when we define that set of VNFs that, certain flows should be going via. For example, here, just to give you an example, let's say that I have a traffic which will go via this network function virtualization 1 and then process it at network function virtualization 2, and then it goes to the service and probably it has to come back. But then I have a budget in terms of end-to-end latency, which should not be exceeded, for example, less than 10 milliseconds. So here I could place these network function virtualization at these edges, which are actually sitting with this kind of optical switches. But then I have options of how to set up the connection, how I can make sure that the flow go either via existing connections, or I have to create a new light path or new wavelengths and so on. And of course, whenever I do this, for example, if I do it in this way using existing connections, that means I'm not creating new light paths or new wavelengths, but that means I still have to do some kind of optical to electrical to optical conversion, which is happening here and happening here, and that will add to the latency. So yes, I will minimize the wavelength or the light path, but I will probably lose in terms of latency. In another option, I could just, for example, create new connection by having completely new light path, which is operating a different, wavelength, and then it goes all the way from here, and then I will gain in terms of latency. But then, of course, it comes at the cost of setting up a new light path session. So here, what we would like to say is, it is very important to understand what is the requirement of the service and what is the objective of the strategy that you are adopting. For example, you can minimize the number of nodes or the number of hops. You can minimize the light path. You can minimize the wavelength. And depending, on the objective that you have in mind, you can, for example, here, what we show that at least, the strategy that we have, we could achieve the design goals that they have, but always we have to make sure that we are within the budget of the latency which we are looking for. And of course, we're not looking into the problem for only one single flow. We are looking into the problem for multiple flows that will be sharing, this optical network, and then the problem becomes much more interesting. Cost is also something which is very important, because if I want to set up, a service function chain, for example, let's say that I want to have traffic going from this router A to this router or to this node, which is H, and I have the freedom of putting my service function chain maybe here, here, and here. But then if I look at the cost, for example, here, this is more expensive, or this one needs to be saved, for other flows and so on. So if I take into account the latency as well as the cost, then the problem becomes, academically speaking, much more interesting in deciding where to place these VNFs. So I can always, of course, have accept the maximum number of service function chain requests, meet my end-to-end or deterministic service requirements, but at the same time I want to reduce the cost for me as a user, but also maximize the resources or minimize the inefficient utilization of the resources, so I can actually maximize the profit of the operator of the network. So these are just like few issues that we've been looking into, and I didn't want to go into too much details about the academic work which have been done there, but there are lots of interesting models that we have used, so we can solve the problem. Just to conclude, to achieve this deterministic latency, in my humble opinion, the routing or the networking that we have been doing so far is not good enough. And definitely we need to look into how we can select, as I have showed you earlier, how we can select how to deploy the service function chain, which is set of functions that will be used to process, certain packet, how we can select even the queues within the switch, how we can select the links in a bundle, and how we can reflect the computation itself, the latency which is demanded by the computation itself into that end-to-end latency, because for me, the latency is not only restricted to the network or the transport latency, but there is also the processing which is needed by the cloud nodes. And here there are lots of interesting things happening, in IETF, for example, segment routing, semantic routing, dynamic casting, and these are solutions which could be, of course, they have advantages. They have also some kind of disadvantages. But the question is that good enough, or do we have to think about completely a new way of defining the IP itself, the IP networking? That's a big question mark. I know that there are lots of researchers that are looking into this problem. And in my humble opinion, this is a very, very interesting research problem to investigate, at least in the context of networking. So with this, I come to the end of my keynote. Definitely, we have achieved certain aspects of cloud nativeness, but the true cloud nativeness, it's still there is a long way to go to take it, to achieve it, and I hope that we can do that while taking this journey of 6G. I have demonstrated to you how we should be thinking beyond the old way of network of networks towards achieving a system that can really seen as a service of services. DevOps is something which has been used and it has been proven to be very efficient, for the design of applications. It needs to be extended also to the concept of networking, since we are talking about networks that are also provided as service, network service. And even if we play with these flexibility that we can get from cloud and deploy the stuff at the edge or near edge or extremely near edge, still we have lots of work to do at the networking level, at the transport network level, so we can meet those extreme low latency communication requirements. And there are lots of things to be done, like adopting the concept of deterministic networking, software-defined queuing, as I have introduced earlier. There is need to think about tight integration with transport network, segment routing, maybe semantic routing, and maybe even probably redesign the whole internet protocol stack. So with this, I come to the end, and I thank you for your attention. And maybe I can receive questions, or at least go back to you, Yusuf.
Okay, thank you, Tarik. That's a very insightful information about beyond 5G. We don't really call it 6G yet, right? Perhaps you can highlight that, because I think that's one part. But some people may want to know why you actually put that says, instead of saying it's a 6G, you're actually saying it as a beyond 5G. Perhaps you can highlight that on that part.
Yeah, well, I mean, I am an academic, and 6G is something which is going to be defined by the relevant standards development bodies. So, we always wait till these SDOs call the system as 6G. But definitely, whatever we do now, it's called beyond 5G. So beyond 5G is correct, because it's not the 5G system that we are having now, or we will be having maybe even in 1 or 2 years. So all the research that we are doing, it's going to be brought to beyond 5G. Is it going to be implemented in 6G as some people see 6G as the system that will be deployed by 2030, even if it is just nowadays service plus a little bit of alpha and beta, or it's going to be brought to 7G. That's something that maybe only time will tell. But as I have mentioned in the beginning of my keynote, there were lots of things that were actually envisioned for 5G, but they could not be achieved in 5G. And now they are actually going to be brought or maybe materialized in the context of 6G. So whatever we may think of now as 6G could not be fully done, for 6G. Probably it would go for other generations. And it's not only technological. It's also there are lots of factors, as I mentioned in the beginning: regulation, business, immediate return on investment, and so on and so forth. So there are lots of factors that play very hard, in defining the technology.
Yes, I couldn't agree more. I think that as researchers, we know how not easy it is to actually promote some new technologies and try to convince people to actually adopt it, especially at the standardization body. And let's look at, I think there is one question from Dr. Kaizuran. Let me show you on the stage. It's already on the stage. At the beginning, you showed us 6G at 0.1 millisecond. Can this be achieved in practicality and reality?
Well, I think when I mentioned that, I was saying that we are just doing, in my humble opinion, the same mistake we did in 5G, because when we defined 5G, we just applied this multiplication or division operation on the requirements of 4G, and we said, okay, this is 5G. So, I mean, can it be achieved in practicality? I would say yes. Yes, in certain scenarios, like, for example, when you talk about these robots within a certain industry 4.0 environment that have to really synchronize using time-sensitive networking and so on, yes, it can be achieved. But am I going to achieve 0.1 millisecond for my phone connecting with the base station here so I can do some augmented reality or whatever? I don't think so. My personal thinking, I don't think so. But and more than this question, can this be achieved in practicality and reality? I would even answer the question by another question: is there need for it? When there is need, we will achieve it. When there is really immediate need for it, I think all those companies that are actually in this telco world, they have the human resources to do the technology when there is need for it. But when there is not much need for it, then nobody is willing to invest resources for something which is maybe it would take time till it would become needed.
Okay, thank you very much for the answer. Let's see if there is any other questions. For the audience, we have about 23 people in the session. If any, there's someone that raised his hand, Abir Abdallah, so I'll hand you the mic.
How to handle energy awareness in beyond 5G?
Yes, so you can see the questions there. Yeah.
Well, I mean, sometimes energy awareness can be dealt with in the design itself. And I just will give you one example. If like, let's say that we have an edge cloud, which is very close to me, for example, or to a certain location. And in that location, there are lots of people that are actually watching, interested in certain video. For example, let's take the example of this conference. Now, I have the conference. Definitely, I didn't check, but most of the people that are in the session, they are probably from Malaysia, right? So if I store the application itself that is processing this video and the streams, if I store it in San Francisco, for example, probably I don't know which tool that you're using. If I store it in San Francisco, that means my stream goes all the way to San Francisco, and then you are consuming it in a unicast way, in Malaysia. And definitely you would agree with me that more packets are traversing different routers, different networks in the world, and that will consume lots of energy. But if I take that service which is hosting this application, this cloud, this conference, and I host it in an edge server, which is, say, in the university where most of these people attending, they are residing, then, the communication will go just to them and come back. So it will be much shorter path, for the communication, and that will save a lot of energy, in my humble opinion. So we could achieve energy awareness by design of by doing the right deployment, putting the stuff in the right location of interest, and then maybe could be some other stuff in terms of maybe for example, if I use this example of conference, that I can do encoding, decoding, at certain rate, which where the quality of experience is good, but then I'm not sending high definition video, which will just require too much processing and too much. My answer is the energy awareness or efficiency can be also achieved by the design of the application. And with this concept that I have mentioned, when I decide where to deploy and how to deploy things, at least I do have the flexibility to reflect energy awareness in the design of the application or of the network, which will be delivering the packets of the application.
Okay, thank you for the explanation. I hope that explains to you, Abir Abdallah. Okay, any other questions from the audience? I have one. I think when people are talking about cloudification and softwareization, people will be thinking about security, of course, right? So how much the data security will play an important role when we're talking about not just on the latency, but also on the cloudification where everything will be everywhere, right? So rather than being at one local place or somewhere that is easier to control and so on. Of course, we do have encryptions and things like that, but when there is too much data and too much things to be controlled, how much security will play a role in a beyond 5G kind of communication, because it's no longer physical. Everything is software.
Yeah. So we've been actually, security is a very important topic, and it's becoming more and more actually important. And you're absolutely right. When you are running systems that should be very secure on systems that are quite open, there are security flows which will emerge. And I think there are lots of research work which is happening there. I mean, I'm involved into certain European consortia where we look into this problem. Actually, security, with this cloudification, we would be even seeing different types of security problems. For example, economical security attacks. What does that mean? If I have, let's say that I have a network slice with certain function, which is sitting on a server, and the same server is being used by another network function. So if I attack this, for example, if I attack this this slice or this network function, which is on that same server, I would cause actually problems to the network function which is running on that server here. And then whatever AI model that probably I would be having, this would increase. This would think that actually I don't have enough resources, and it would need ask for, you know, auto scaling, more resources. And that actually will probably cause, you know, some kind of high bill, you know, to the owner of the second network slice. So admittedly, with this network slicing or with this network softwareization cloudification, different security problems will emerge. People are working on them. New types of security attacks will emerge. As I said, this economical denial of service will emerge. And these are also people, they are looking into them. But at the same time, I see, for at least in my humble opinion, this network softwareization is also a solution to some security problems that we were dealing with in a traditional way that was taking even longer time. And we have been looking into this thing in the context of another project which is called Anastasia. How how this network softwareization helps in security. For example, if I have, let's say that I just start being suspicious that somebody is under attack. So the drastic measure is actually you just go and you block the traffic to that person. And probably if I do this, this will cause me will support even the attacker in his or her aim, which is basically denying, the service to that person that I suspect being under attack. So when I use, for example, if I use SDN, I could say, okay, let the traffic go to the person that I am suspecting that he's under attack, mirror the traffic, send it to this kind of VM, virtual machine, where I would run, for example, an IDS, like intrusion detection system, a virtual one. And then I check there the packets and make sure that there is when I am really sure that there is a really serious problem and somebody is attacking this person, and I do this in an on-demand way, in a software way, because I just say to the SDN, please copy this, mirror this traffic, send it to this VM which I have created. Then it gets processed in the packets. And then when I decide that there is really a problem with certain person attacking or a group of people attacking, then I will just send the rule again to the SDN switch, and they say, now let the traffic go, but block these kind of flows that are coming from these specific IP addresses or from these specific domains. So here I use SDN and I use NFV, this kind of enabling technologies of network softwareization, so I can take quick decisions on dealing with the security problems. If I do it in a traditional way, then I have to send an engineer, set up a firewall, have a traffic. It will take time. So what I want to say with cloudification, we will definitely see more security problems, and this makes this research area very, very appealing. But at the same time, it is also an enabling technology to deal with certain types of security attacks in a very quick way.
Okay, thank you for the great explanation. I think that really relates to what we're talking about on the networking, on the softwareizations, and also having less physical as what we're doing now, right? Okay, so I think there is no more question coming from the audiences, and then I think time we have slightly off the time, so it's about 10 minutes. I think it's not it's not a problem. As a token of appreciation, before we end this session, we'll present you a virtual token of appreciation. Since everything is virtual, let me play you with a video. And this is also for
So thank you. That was nice.
So with that, thank you very much, Tarik. I think it was really great to have you with us for the APCC this time around. Hopefully, when we have physical conferences, we can have a lot more meetings and a lot more discussions on the issues. Right?
Looking forward to that. Yeah.
All right. And also, I would like to thank all the audiences. I think Prof. Yang Yang is also still there. So thank you very much, Prof. Yang Yang. To all the others, don't forget, we still have another session tomorrow. Let me see. Prof. Yang Yang, handing the mic to Prof. Yang Yang if he wants to say something.
Yes. Thank you very much, Tarik, and also the chair for organizing this keynote. It's very, very hot topic. As I mentioned, 2020 is a special year for 5G, and now we are on the journey to 6G. So, Tarik, you are leading us towards 6G.
No, Yang Yang, by the way, it's very nice to meet you, and I hope that we can meet again, face to face.
Certainly.
Yeah.
Okay.
I enjoyed it.
Thank you very much. Yeah.
Okay.
Enjoy the morning sun in Finland.
Yeah, we're about to go for our dinner now. Okay, for the rest of the participants, please join us again tomorrow. We'll have another 2 keynote speakers. We have Prof. Tarik, Prof. Khalid Lataif, and also Prof. Haris Ghassanin in another 2 interesting topics tomorrow, as well as the presentations of the papers. So once again, thank you everyone. Thank you, Prof. Tarik, and also Prof. Yang Yang for the very nice keynote talk today. All right, see you. Have a nice day ahead, everybody.
Bye-bye.
Bye.